Dynamic modeling of sensitive heat storage device integrated into an energy system. Introduction. In thermal energy storage, TES, the used matter gains energy in the phase of heat storage when temperature increases and loses it in the phase of heat recuperation when it decreases. Thermal energy storage is much cheaper than chemical storage. In the future energy systems, with high amount of intermittent renewable energy sources, the importance of TES is due to the fact that half of the total final energy consumption worldwide could be attributed to heat. The integration of the storage tank in energy installation is difficult, both in the design phase and in the operation of this installation. In addition, it will be necessary to assess their annual or seasonal energy consumption. To meet all of these requirements, the use of dynamic modeling and simulation of energy components and systems became unavoidable. Methods. RELAP 5 software is well known as one-dimensional steady state and transient code used in the modeling and simulation of thermodynamic systems, especially in nuclear reactors. The code was used to simulate a water storage tank for thermal energy storage. The used methodology was adopted by Terzibatian based on Modelica code. It consists to discretize the water tank into small volumes in radial, angular, and vertical directions. This method was applied on a vertical cylinder of height h and diameter d, which represent a form of storage tank which is quite widespread on the market. The study domain is discretized into a finite number of control volumes, as shown in Figure 1. This geometric decomposition was chosen in such a way that all the control volumes have the same volume and the same horizontal exchange surface. In the left, the vertical discretization of the tank into 8 layers. In the middle, the radial discretization of the tank. The radius of each cylinder is calculated by a formula. In the right, the angular discretization of the tank. The angle of each portion is calculated by division. Results. This figure presents the variation of discretized tank layer temperature as function of time. Results show that the bottom layer temperature decreases rapidly as the cold water enters the tank from the bottom inlet. The temperature of the top layer has preserved heat during the first 1000 seconds in case of high mass flow, since the temperature stays stable near 70 degrees. In the case of low mass flow, the top layer has conserved the hot temperature until approximately 5000 seconds. This figure presents the temperature of water in outlet pipe. Results show that the difference temperature does not affect duration of hot recuperation. After that, the temperature decreases until reach the cold value during around 2 times the first duration. Conclusion. In this work, an approach for modeling and dynamic simulation of a water storage tank was studied and discussed. The presented approach provides a fine modeling which makes possible the prediction of the heat transfer and flow mechanism within the tank. To carry out this prediction, it is important to perform at least hourly simulation component and complete system operation. This work could be enhanced by integrating climatic data, usage data, and energy specification of the equipment, which could be the subject of further works. The study demonstrates that the use of dynamic modeling and simulation of energy components and systems is therefore becoming essential.